Hello and welcome back to Neural Networks from Scratch in C++. In this video we're going to finally code the more efficient matrix multiplication, and we're going to compare the performance with the original. So what we're going to do is we are going to make pretty much a function with the exact same template, and it's going to be called matmul instead of naive matmul. And we are now going to copy this and implement this in the TPP file. So let's do that over here. So recall, in our new matmul, we are going to have the first matrix be in row major order. Our second matrix will be column major, so that means that this will be contiguous in memory. These will be contiguous in memory. And then we are going to be iterating over our columns one by one and keeping the first row fixed. And then our output will be in row major, so that by iterating over the columns here, that means that each output will get stored, I guess, one by one contiguously in a row of the output. Okay, so let's try to code this out. So because of the fact that our first row here will be the last to get updated, we're going to have it be the very first for loop. So that's how it works. It's like the exact opposite. So what we're going to do is we are going to iterate over nr, after which we'll iterate over c, oops, typo, and then we're going to iterate over I. And one thing to notice is that now our matrix B is not going to be inner by NC because of the fact that it's column major. It's going to be NC by inner, right? Because we're going to have the inner dimension be contiguous. Okay, so that's really important here. Okay, so now what we're going to do is we need to make an output, so exactly the same way that we did it in the naive matmul. And there's a trick. By doing this, this initializes all the data to be just zeros. Okay, so instead of me having to one by one assign zeros in the loop. Another trick that we're going to do is we are going to take const references of the rows. So in this case, or the contiguous data. So now we're going to take a reference to this row. And the reason we're going to do that is because it's just a lot cleaner to represent the dot product as a dot product on two vectors rather than having like this gross indexing into two dimensions notation. So what we're going to do is we are going to get a at r, and the same way that we do that, we are going to get our second matrix. We're going to get a column from it. So b at c. And now we're also going to do the same trick for the output, but it's not going to be constant because we're updating it. So we're just going to get a reference to the result row, and this will be our result at bar. Okay, next we are going to make an accumulator, and the accumulator, we're going to accumulate onto it a row at I times b call at I. And then finally, we are going to store the result in result row at c is equal to our accumulator. And then finally, we're going to return the result. Okay, great. So let's try compiling and see that there are no issues with this. So that compiled great. And now let's make some simple timing functions. I'm not going to make it like templatized and clean. I'm just going to make some quick and dirty timers. So we're going to make a function called time naive matmul. And here we are going to make a matrix of some size. So what I'm going to do is, because these are template arguments, I need to make a const x per variable. And I'm just going to call it dim. And let's say we started at 50. And every single dimension will be the same. So we'll make dim by, and we'll make it an integer matrix for now, but we're going to play with different types later, and we're going to make it, we're going to call this A. We're going to make a matrix and put in 0. And actually, I want to clean this up. I'm going to make this be auto. This be auto as well. And I'm going to call this B. And I'm going to put the templates over here. So dim int. And then we're going to iterate over some number. So I'm going to call this loop count. And let's start at, let's say, 100. And then we're going to do our naive matmul with A and B. So let's first see that this compiles. No issues with that. And we're going to use the chrono library to do our timing. So what I'm going to do is I'm just going to look up chrono time just to get a reference on how to do this. So we are going to, okay, so what we do is we get a start time, we get an end time, and then we are going to see out naive matmul took, and then it looks like we get the elapsed seconds, so we're going to put that above, and we call the count method to get the number of seconds elapsed. So it took this many seconds. We're going to end up. And this should not be count, this should be cout. Okay, so this should be elapsed seconds here. Okay, great. And now let's try doing a simple timer. So we're going to, essentially we want to comment all this out for the time being. And we are going to call time naive matmul. And we're going to run it. So you can see that with a 50 by 50 matmul, so A is 50 by 50, B is 50 by 50, and we iterated over 100 times, we are seeing that it took about 0.18 seconds. Okay, so that's with 50 by 50. But let's increase the size. Let's run this again. So we doubled the size, and ooh, we doubled the size, but now we increased by a lot more in the number of seconds. Let's try something else, maybe 150. And running this, and it's still running, 4.2 seconds. What about 200? Oh boy, it's taking quite a bit of time. So while this is running, let's start, well, you can see 9 seconds. And I'm going to now do 500, and this is going to be what I'm going to be comparing with the new matmul. So let's make a new function, and we're going to call this time matmul. And I'm going to copy pretty much all of this, and I'm going to replace naive. I'm just going to call it matmul, and this won't be naive matmul, it'll just be matmul. So one thing to keep in mind is the fact that, well, right now I'm just making a random matrix B. But you know that if you were to actually use this new matmul, you would need to ensure that the contiguous data in B is actually column major, so that the columns would be contiguous. So we can make a little test case later to actually check for that, or actually we can do that right now. So this is still running, and I'll let it run. But going back to Excalidraw here, essentially imagine my create matrix function makes me a matrix that is row major. Okay, so there is actually an operation that we can do to ensure that the data, that the columns are contiguous in memory. And what we can do is something called transpose. So the operation transpose, the idea here is that if we have data that is contiguous like this, by doing the transpose operation, essentially what you do is imagine you're flipping like your phone. So if your phone is screen down and the top is like, say, over here, right? And now let's say that you flip it, so now your screen is facing you and the top of the screen is up here, okay? So let's say your top of the screen is over here and it's face down. Now you flip it in such a way that the top is up here and the face is towards you. And then what you're going to do is you're going to see that now the arrows are going to be going down. Well, the arrows are actually going to look like this. Okay? Okay. So essentially what this is going to do is it's going to make the columns be contiguous, right? So now the data is going in the column direction, essentially. Okay, so let's go back here, and oh boy, this is still running. That's great. Let's now write the transpose function. So transpose is just going to take NR NC. And oh boy, okay, this took 3 minutes to run. That's fantastic. So transpose is going to return a matrix. So instead of returning an NR by NC, we're going to be returning an NC by NR matrix. And it's going to take a NR by NC matrix as input. Okay. And so let's make this matrix. So it's going to be NC by NR by T result. We don't need to initialize it because we need to update every value anyways. So we're going to iterate over the rows. And we are going to now, so at position, so let's say that we're going to be flipping every value. So pretty much the idea is that instead of at R at C, we're going to be indexing by C at R, C and R, and matrix at R at C, and then returning the result. So this would be a good exercise for you to draw this out, try to understand this, and then try to draw out the algorithm, or try to figure out the algorithm yourself for doing this transpose. But the basic idea is that all we want to do is we want to swap the rows and the columns. And that's the basic idea. Okay. So now this, assuming you believe me, does that. If you want to verify it yourself, you should definitely do that as an exercise. And now we're going to also put this as, I want to put this in the header file as well. So let's do that over here. And let's just do a simple exercise. And what we're going to do is we're going to make the matrix A. And then we're going to say AT for A transposed is going to be transpose of A. And now we're going to run the print matrix. And let's do it on A, and then C out and line to make some space, and print matrix of A at T. So let's run this. No matching call for transpose. C. I'm curious why it can't infer the template arguments. Either way, let's just fill these in. But let's see, maybe there are some other, there are a bunch of errors. I see, so there is a size type I have by accident, which should be size T. And I probably, I have the same bug over here. Okay, so let's clear and rerun, see what the results are. Matrix does not name a template, but is followed by, let's see. So let's just listen to the compiler. Rerun, call to mapmul is ambiguous. Okay, this is great. So many different lovely errors. So call to mapmul is ambiguous. Let's make it dim. Okay, run it again. So many lovely errors. Does it have anything to do with this? Candidate template ignored, invalid explicitly specified argument for template parameter NC. I see. So this was going to be NC and inner. And now I'm going to go back here. I don't need any of this. And now all of my problems should go away. Okay, great. So now we have the time mapmul. So we just compiled this, and now we should be able to print A and then print A transpose. So let's run this. And as you can see, before the rows were contiguous, now our columns are contiguous. So we iterate over 0, 2, then 1, 3. And of course, this is a small example. So what we could do is we can make this slightly bigger so that you can see that, well, it's not a perfect way to test. At least you can get a better intuition that this is correct. Okay, so you see here that we are now iterating over the columns. So 0, 3, 6, followed by 1, 4, 7, then 2, 5, 8. Okay, so now in our time mapmul, what we're going to do is we are going to say that B is transpose of create matrix. Okay, and we have an unused variable. That's because we're not printing these anymore. So I'm going to comment those out. And before, you saw that we were seeing something like 3 minutes on the naive mapmul. So now I'm going to run the time mapmul function, and I'm hoping for a lot better than 3 minutes. So this is running now. So let's do, I guess, a bit of a review. So right now, because of the fact that we're storing our data, we're always storing our data contiguously. So even the second matrix, the columns are contiguous, and we're storing our outputs contiguously, right? Because of the fact that we're now iterating over the rows. So we're expecting to get a much better performance over the naive 3 minutes that we were getting before. But even still, maybe this dimension is a little bit too large. So what I'm going to do is I'm going to kill this, and I want to come up with a smaller dimension for the time being. And if you want to play around with the code for larger dimensions, you can definitely do so. But I'm going to change it for both of them, and I'm going to run this again. So I'm now running with a dimension of size 200, and we get 4.485 seconds. I'm also going to include the naive mapmul in this and run both of them. So this is definitely more than 5 seconds right now for the first one. So about 8.6, and by rerunning this again, we're seeing 3.4. So there is some variance. So let's maybe make the loop count a little bit bigger. And rerun this. and it's really taking its time. But we should see about 15, 16 seconds for the first, okay, 19 seconds for the first. And if it's going to be consistent, we're going to see about half the time, even less than half the time for the optimized matrix multiplication. So obviously this is all well and good, but standard compilers, if you add the O3 flag, so I'm going to find that over here. So if I compile with the most optimized matrix multiplication, you can see that if I run both, that even though the second one is still a lot better, if you look at it, like you're talking about 6 compared to 9, we went from 19 seconds in the unoptimized matrix multiplication to like, what is this? This is 1/100 millionth, I think, of a second. So yeah, huge improvement by just including the compiler optimization. But let's run this again. But you can still see that we're always better with the optimized one. So when we're talking about doing a bunch of these different operations, even though the compiler is going to do a lot of the work for you, in this case most of the work, in all cases we're seeing that the second one is still faster than the first one. Okay, so I think with that I'm going to stop. And now we're going to go back to, I guess, some of the more neural network related topics. Right now this was, of course, really relevant that we go over some of the basic performance optimizations, since this is such an important primitive in neural networks. And we're definitely going to come back to these types of discussions, but I think I'm going to leave it at that for the time being. All right, hope to see you in the next video.